my name is Patcharaporn. Today I will present our project name is Superconducting Magnetic Energy Storage SMES with my teammate's name is Nattawas. His student ID is 64105508880. So our table of contents is appear like this. I will start from the first one is an introduction to SMES technology. The first one is history. The first his story is happened in 1969. It is the concept of purpose. The idea of SMES was first introduced by Ferrier in France, suggesting the use of superconductors to store the energy in a magnetic field with zero resistance. The second one is in 1971, the first prototype developed in the University of Wisconsin in USA launched one of the earliest research programs relating to the first SMES prototype. It demonstrated rapid energy discharge and potential for grid stabilizations. The third one is late 1990s. The high temperature superconductor or HTS became emergently a variable, reducing cooling costs and making SMES more practical and compact. And the last history is in 1997. First grid connect between HTS and SMES. American Superconductor Corporation developed the first large-scale HTS-based SMES connect to a power grid in Germany, proving its real-world application for power quality and stability. And the second one is our advantage. Its high efficiency and fast response time. SMES system achieve over 95% efficiency by storing energy in a superconductor coil with almost zero resistance. They can respond to power demand charts in milliseconds. Environmental impact stability. These systems are eco-friendly, emitting no greenhouse gases or using toxic material. They maintain stable performance regardless of external conditions like temperature or weather. The reliability and longevity. SMES systems have no moving parts and use durable superconducting materials, resulting in less wear and tear and lower maintenance costs over their long lifespan. The last one is scalability and versatility. Capable of storing energy from few kilohours to several megahours, SMES units are flexible for various applications and can be installed in diverse environments with minimal modifications.
So first of all, what is a superconductor? Superconductor are materials that can conduct electricity without resistance when cold below a critical temperature. So if you take a look at the bottom left graph, the horizontal axis is the temperature, whereas the vertical axis is the resistance. So this graph will show you how superconductor react when it reach the critical temperature. So the resistance of superconductor will significantly drop to zero when it reaches the temperature, whereas the non-conductive material will continually decrease. So for the other effect, which is Meissner effect, this effect will expel all the magnetic field from its material. However, this effect isn't related to our system. So this slide is the explanation of how superconductor react when it reach the critical temperature. So if you take a look at this video, after the temperature drop to the critical temperature, and when the negative charge fall to the material, it will magnetize the positive charge. Also, when it reach the critical temperature, positive charge will be more stable, and then the negative charge will magnetize the positive charge to create a higher positive charge area. This area will conduct the second electron that shares the positive charge, and this will create the Cooper pair. Cooper pair are responsible for zero electrical resistance. Then let's talk about our system, which is superconducting magnetic energy storage system, or SMES. So in SMES system, energy is stored in a conducting coil magnetic field generated by direct current. When current flows to the conducting coil, a magnetic field is created. According to the magnetic theory, the energy stored in magnetic field is proportional to the square of the current and coil inductance, as the equation that we show you over here. This formula is based on Faraday's laws of electromagnetic induction and the work energy principle in physics. It specifically represents the magnetic potential energy in an inductor. So in this system, inductor is superconducting coil. Then let's take a look at how energy flow to a superconducting magnetic energy storage system from input to output. First, the AC current from grid is converted to direct current using rectifier, which typically use diode. This system is essential because the conducting coil in SMES is only operate with DC current. Next, the convert DC may have some ripple to ensure a stable current. Filter made of capacitor and inductor are used to smooth direct current. This prepares for safety and efficiency of this storage system. Then for the third step, after the DC current are cleaned, stable DC will flow to the superconducting coil. Because this coil have zero resistance from superconductor principle, the current will generate a magnetic field without energy loss. This is where electrical energy is converted into the magnetic energy and stored. So in this method is the charging process, and which is can explain by this equation over here. So when the fourth step, when the energy is needed, the current in the coil is gradually reduced. According to the Faraday laws, this charge in current induce a voltage, which can explain by this equation. This cause the magnetic field to corrupt and release the solid energy as DC power. So this is a discharging process. And then finally, the release of direct current is sent to the inverter, which switch the current direction rapidly to create AC. This AC is synchronized with the grid voltage and frequency before it delivers to the power grid outload. So overall, SMES convert grid electricity into the magnetic energy for storage, and then back to AC power quickly, efficiency, and without degradation.
And this one is our applications of superconducting magnetic energy storage. The first one is mass transit system. As you can see in the picture, rail network and urban transit system improve power efficiency and reliability with SMES. This unit manage energy produced during baking and redistribute it efficiently, enhancing the overall energy efficiency of the transit system. The second one is electric vehicle charging station. With the increasing adoption of electrical vehicles or EVs, the demand for efficient and fast charging solution is rising. SMES system at EV charging station manage long demand by storing energy during off-peak time and realizing it during peak demand. This reduces strain on the electrical grid and enables faster charging times. And the last one is renewable energy integration. The renewable energy source like wind and solar introduce variability in power generation. Due to weather conditions, SMES systems stabilize the grid by quickly absorbing excess electricity during high production period and release energy during low production, smooth out fluctuations, and enhancing grid stability. And this is all of our superconducting magnetic energy storage or SMES. Thank you for your listening.